YouTube. Okay, then welcome everyone to the weekly colloquium of the Physics Institute of the UNAM in Cuernavaca. Our guest today is Dr. Alessandro Corvetta. Let me say some few words on his vitae. Alessandro Corvetta is an assistant professor at the Department of Applied Physics at Eindhoven University of Technology in the Netherlands. His research activity is at the interface between complex flowing matter, physics for society, and machine learning for nonlinear physical systems. Since 2013, in the context of the crowd-flow topical group, his goal is to advance a fundamental understanding of pedestrian crowd flows. Dr. Corvetta graduated in applied mathematics at Turin Polytechnic University in Italy in 2011, with a work on high-performance plasma simulation conducted at Los Alamos National Laboratory. He has a PhD in applied mathematics from Eindhoven University of Technology and in structural engineering from Turin Polytechnic, both acquired in 2016. Alessandro, thank you very much for joining us today, at least virtually, and we are looking forward to your talk.
All right. Thanks a lot for the very nice introduction. So I hope you can hear me, that my screen is visible. If there is any technical problem, please let me know. So, all right, let's see. Good. So, well, first of all, pleasure to meet you all virtually. I am this guy. I hope you see my mouse. So I am talking to you from the Netherlands. So we are, let's say, in the middle northern Europe over here. And what I'm going to present is a work that it's running over here at the Eindhoven University of Technology, and specifically in the group of fluid mechanics since about 2013, with a bunch of collaborators. The main ones are here: Federico Toschi, Roberto Benzi, Cas, Chungming Li, Alessandro Gabbana, and Adrian Muntean, plus tens of students. And the purpose is to shed some light from the physics perspective on the flow of this very special system, let's say, that are human crowds. So our work is somewhat at the interface between fluid mechanics and more like statistical physics. So, said it in other terms, let me try to have my pen here. Let's see whether I can do it. Yes. So the point is, given this very special system that are human crowds, so these aggregates of pedestrian moving, the purpose is to achieve some degree of quantitative understanding of the system. And so major question is, okay, what does it even mean achieving a quantitative understanding of this system? So before entering in the question, what does it even mean understanding crowds, let me mention why it's something very important. So clearly, understanding crowds means the capability of designing better, for instance, civil facility like airports or train stations and such, as well as having the capability of designing and possibly predicting more dangerous events that from time to time, unfortunately, still happen. And I must say that this will be certainly true in Europe or in Central Europe. There is a growing pressure from society to increase our understanding of crowds, given the fact that many of European countries that are densely populated, like the Netherlands, like Switzerland, and so on, there is generally a forecast that facilities such as train stations or airports will see an increase in pedestrian load that is of about 40% within the next 10 years. Well, actually within 2030. So this means having the necessity of managing substantially more people than we do now. And the issue in Europe is that although we need to manage more people, the space is generally over. So we cannot fix the situation by just making some, bigger facilities like larger station and so on. The space is finite and is finished. And so we need to make space smarter. And that's why understanding crowd is important. So we want to smarten our environment to be able to guide, to nudge more people, to have them always feel safe and comfortable in the environment. And so understanding the behavior of the system is crucial. Now, having said that, if we think about crowds from the physics perspective, what do we have? I would say we have a flowing system. So, I mean, if we think about the crowds, we can think about this aggregate of pedestrian moving, and overall we have a flow. However, this flow is not of classical particles, whatever, water molecules, or whatever you have in mind. We rather are talking about active particles in general. So particles that have the capability of converting internal energy into motion, and this happens in a, well, clearly very variable and stochastic ways, because everybody would move according to personal will. So we move because we need to reach our destination. We sidestep because we want to avoid someone. Some people prefer to stay closer to others. Other people would prefer to stay farther away. So we have extreme high variability in the system. And so, again, we are dealing with a physical system of active particles that flow, that is highly stochastic. And so this brings the question, what does it even mean, understanding these systems, or possibly making a quantitative prediction of such a stochastic system. And what I'll be discussing, in the talk is a little bit the perspective that since few years we are building on the problem, that is try to understand and try to make models that reproduce features of the system that are somewhat universal, that are somewhat observable, regardless the very fine details of the system, the very fine composition of the crowd, and so on. So these are somewhat features that robustly appear in the system, and this is what we target with our model, and this is what we want to be quantitative on. So again, then the question becomes, which features are good features to be targeted in our models? And as we will see, this feature are, well, statistical feature of the crowd system. As we will see, we would like to have models that instead of trying to mimicking in a sort of point-wise perspective the behavior of the crowd, like predicting what each person is doing, this will be about models that reproduce the behavior of the crowd at the statistical level, in the sense that each particle would move providing probability distribution that are the same of the physical worlds in terms of velocities, in terms of distances, accelerations, and whatever. Now, yes, so as I said, imagine that we are considering, for instance, one person crossing a corridor, and we want to model this behavior. Well, I think we can easily agree on the fact that it would be, almost impossible or practically impossible to come out with a point-wise model. I mean, some sort of, let's say, ordinary differential equation that, point by point would reproduce the exact trajectory of this person. So let's say reproducing feature of specific individuals is probably something out of the game, especially if we want to be quantitative. And so the take that we have on the problem is, again, as I said, aiming at reproducing a feature of the ensemble, so statistical features of the crowd system. Well, what does it mean? Well, understanding, modeling, reproducing features of the ensemble. Well, first of all, to be able to even understand or model, we need the possibility of observing the statistical feature of the system. And to observe such features, first of all, we would need data, so measurement of how people move. But since, as I said, the system is so extremely stochastic, well, it's not about observing, our crowd system in terms of few trajectories. It becomes about observing our crowd systems in terms of millions of trajectories. Because if you have such a stochastic system, the only way to extract feature from it is to have the capability of really resolving the statistical, the statistical portrait of the system. And this can only be done once one is able to, single out, for instance, what are the typical behavior of the system. So what are the average behavior? What are the typical fluctuation around average behavior? What are the rare events? And so on and so forth. And so this can only be done by having very large data set, say millions of trajectory, and unavoidably such data sets need to be acquired in real life condition. And of course, as it happens for all physical systems, we would like measurements to have very high accuracy, very high resolution in space and time. Well, this has been our starting point to analyze the crowd. So we want to understand this very complex system. We need data. The system is stochastic, therefore we need a lot of data. And this is where we started in about, as I said, 2013. Let's say before our work, all the research about crowd dynamics was generally performed in laboratory conditions. So these are pictures from a project run here in Europe by the group of Armin Seyfried at the Jülich Supercomputing Center. And here you would say that you would see that they are investigating the behavior of, for instance, a crowd moving into corridors in case of having, for instance, counterflow conditions. So you have the red people moving from right to left, and the people with the black suit moving from left to right, and then they would investigate in laboratory which kind of flow patterns emerge, and so on. And same goes for this other laboratory scenario. Now, this kind of measurements enable us, or enable them to gather insights on the behavior of the system. However, whenever we work in laboratory, well, we are, limited by the fact that we can deal with a finite numbers of volunteers, of students that basically need to be invited to this experiment at some time. And so this unavoidably, makes it very hard to collect big data on this system. And besides, I mean, when you realize in laboratory experiments that deal with crowd, you always, have to deal with the bias that you are working with people that are asked to perform some action. So the kind of readings of the system that you get are the readings of the actions that you ask your participant to do. So you have some sort of experimental bias. And finally, I mean, even when you invite 100 or 200 students, there would be strong limit in the capability of exploring the statistical behavior of the system. You can explore the average behavior, but definitely, I mean, it would be very hard to get accurate insight on the fluctuations of the system. And so again, this is where we started in 2013. Our purpose was to get into real life scenario and to acquire this very large data set. And so the only way to acquire this large data set is to go in real life scenarios like stations and to start tracking people and gather this big data set. Well, I must say that when we started, the technology to do the tracking in real life scenarios was not even there. And so this was the first bit of our work. So develop some technology that could enable us to go in real life scenarios and acquire highly accurate data, so trajectories about walking people. So this we solved by using a type of sensors that back then was kind of fashionable, and probably many of you have crossed ways with this. And so when we started, we used something that was called Microsoft Kinect. It was used by kids to play video games. So you used to put it in front of a television, and then the sensor could pick the movement of your arms, and this way you could give some signal to your video games. Now the thing is that these Microsoft Kinect are actually very cheap sensors that measure a very, let's say, relevant type of signal, that is the depth signal. Basically, if these sensors are put overhead, like in this picture here, then they would return the distance between each pixel that they see and the camera plane. So they would return scalar field containing distance map. Now, what we did then was to realize the technology to, let's say, extract out of this depth information, trajectory information. So what you see here in this video is a depth field that you can acquire by, let's say, concatenating or fusing the signal from these 4 sensors that I put here on the right-hand side. And wait a minute, my screen is all right. So what you see here in the movie on the left-hand side is the fused signal out of these 4 sensors. And then, well, it's an overhead view, and imagine that the value here of the pixel express distance from the camera plane. This means that the floor is white, the floor being the farthest possible point from the sensors. And then as you get closer and closer, the shades get darker and darker. And so the heads would be the darkest spot because they are closest to the camera plane. And well, I hope that the movie is kind of visible. I see that, you know, you get some sort of compression error, but yeah, sorry about that. I'm not sure whether I can do something about it. But nevertheless, the major point is that with these sensors, we could acquire data in an extremely privacy-safe way, because no people are recognizable in this sort of signal. And this enabled us to start acquiring data. Now, of course, we needed to develop the algorithm to extract the trajectory and precisely to extract the position of the people out of that frame. Well, this is something that with a reasonable density of 1 person per square meter, 1.2 person per square meter is conceptually simple to achieve. It can be done by let's say, clustering algorithm. So let's see if I can get my movie again. Yeah, so imagine you would start looking for contiguous blob in this field, and then this blob would correlate with, or would be people. Now, thing is that, well, the cool thing about this format is that it doesn't need to stop at 1.5 people per square meter, but it's actually possible to do much better. But in that case, one starts needing machine learning techniques. And so what you see here in the movie is, you know, small kids being tracked in front of the door of this museum. These were like school kids, really, you know, looking forward to leave. And so they created like this dance flow in front of the door. And then at a certain point, the teacher would open the door, and then you would see that this flow gets released. But as you can imagine, identifying all the different people at these densities is a little bit more complicated, but you know, with machine learning, this can be easily addressed. And besides, much more information can be extracted from this sort of field, like shoulder orientation, and so like sort of details that are more precise than the individual position. They're like super microscopic level information. All right, now imagine that by doing this, we construct the capability of acquiring data. So in principle, we have the technology, so we deploy the technology in train stations or museums and so on, and we can leave these sensors running 24/7 for months, and then just waiting long enough, we would we would have data sets that are as large as we like, right? And so this is where actually the game can start of, you know, trying to understand quantitatively, as I was saying, crowd dynamics. So now what I want to do in this second part of the talk is just discussing what we can do once we have this big data set. So we have the data, so what? And, you know, as a physicist, I would say, as physicists, what we did was try to get a quantitative perspective on the dynamics, starting from the simplest possible conditions that, although simple, are non-trivial. That would be, let's say, saying something about the motion of the free particle in some sense. And so about the statistical property of pedestrians that will move along without interactions with others. And then when we understand the free motion, then we can start moving from the free motion to the motion in which we have people interacting in pairs. Let's say, which kind of forces do we need to put in order to quantitatively predict the avoidance of people, and then the complexity can grow. So we can start putting, instead of only 2 people, more people, so moving into denser scenario. And actually, I will conclude the talk with with a quite recent work in which we really studied say how the crowd moves, and to do that we moved to a more variational approach, and this is left to the last part of the talk. So without further ado, let me give some details, right, on what happens, what we can do when we have so many trajectories. Now imagine we are studying the simplest possible condition. This is one pedestrians that move across a corridor. And imagine that now we have the chance of observing this experiment of one pedestrian crossing a corridor, not once, not twice, not 100, but possibly thousands of times. All right, so what do we see? Well, let's say that here I put on the right-hand side the probability distribution function of the walking velocity of this person, and then imagine that what I have here is what I can observe when I consider about 250 trajectories. So this is a probability distribution function in logarithmic scale. So what you see here are parabolas. This means Gaussian distributions, of course. And so a person would move with a Gaussian distribution in velocity of about 1 meter per second in the longitudinal direction. And then the person would have a fluctuation, of course, around a transversal fluctuation, of course, around 0 meters per second, with a standard deviation that is, well, more or less of the same size of the longitudinal motion. This is what you observe with 250 trajectories. And now, what if you start looking at 250,000 trajectories? Well, you would observe something that would be very hard to observe in laboratory. That is the fact that, you know, at random, people entering in our corridor would, you know, simply stop and invert their trajectory. Well, this can happen for any sort of reasons, like they received a phone call and they need to turn back or whatever. This is simply something that you reproducibly observe in the dynamics. And so our first challenge was to come out with the simplest model, the simplest stochastic differential equation that could reproduce, again, this very simple behavior. So we went for a Langevin-like equation. I assume, you know what I'm talking about. So a second order stochastic differential equation in which, let's say, our dynamics would be regulated by an interplay of forces that would regulate the propulsion of the person, the confinement in the corridor, and so on, plus, let's say, a random excitation to the system. And then, okay, in the next slide, I would only mention the propulsion part, and then let's skip, for simplicity, other terms that have an influence in the dynamics, like confinement and so on. So imagine that what I said is that we observe people walking at about 1 meter per second that have this random velocity inversion event. So what is the simplest force that could reproduce this? Well, in principle, is a gradient of a velocity potential. So imagine that here I have the velocity axis, and now I'm considering a velocity dynamics that is an interplay between a gradient force and a noise that would constrict the state of the system to fluctuate in general around this velocity well. So this would correspond to people moving at 1 meter per second, but the presence of noise not only gives a small scale fluctuation, but also every now and then gives a larger kick. So we have large deviation in the system that yield the transition from one well of the velocity to the opposite well, and this would give, again, this inversion event. Now, very simple dynamics, but with such a model, we can, well, not only, of course, capture velocity PDF, but what's even more interesting is the fact that we can get the inversion statistics, so the Poisson process with which, you know, the observed people would invert their event. So again, as we observe 3 people entering in our system, every now and then there is one that inverts the dynamics. This is an uncorrelated dynamics in time, so it means that it happens with Poisson statistics. And the good thing is that this model while simply predicting the small-scale fluctuation, well, with the same parameter and actually only tweaking the small-scale fluctuation would also capture the large deviation, so the inversion event. And now, I mean, I will not enter into details, but of course we try to, or we managed to capture multiple statistics as one. So not only the velocity PDF, but also the velocity decorrelation process, the transversal velocity PDF, the transversal position PDF, the correlation in transversal direction, and so on and so forth. So to be synthetic, this is the beauty here is that with a very simple model that is a Langevin with a double velocity, we can capture quantitatively many features of the systems, and more can be superimposed, like the process of the shoulder fluctuation can be included, and this as well can be modeled as a Langevin process as well. But now, as I said, we want to build the complexity level by level, and so we have solved, let's say, the motion of the free particle, and now it becomes about to study how the free particle change the fluctuation process about the preferred path whenever some other person in the opposite direction would come. And so also here we basically were in our train station and we consider all the cases that we could observe in which there was one person walking and another person coming in the opposite direction, and there would be no one else in the surrounding perturbing the dynamics. And we asked what could be, the simplest model that would quantitatively reproduce the avoidance behavior. So, of course, this was about, as I said, introducing forces in the dynamics, and consider that now our dynamics would be characterized by a longitudinal position along a sort of preferred path, a transversal fluctuation around the preferred path, but also dynamics of this preferred path. So the fact that as we see someone in front of us, we would also modify basically the path that we intend to follow and fluctuate around. And so, of course, one needs to introduce forces that would alter this path. And then, we saw that to get a dynamics that is indistinguishable from the data, we needed to introduce a long-range force depending on vision, and also, there is a need of also a small-scale force that models the fact that when really people get into close contact, there is like a snapping behavior that would yield this rare avoidance that you would see in these conditions. Now, again, I will not enter into technical details, but also in this case, we aim at capturing the dynamics quantitatively and which kind of statistics are relevant, for instance, for this avoidance process. Well, in our case, we looked at the joint distribution of distance that pairs of people have when they avoid each other, for instance, considering the transversal distance that they have as they enter in our domain and see each other. So imagine that we put this here as an x at the x-axis of our plot, and here in the y-axis, I would put the transversal distance that they have at the moment in which they are closest in space. So, what you observe is that when the transversal initial distance was 0, then people necessarily have to sidestep, and then on average they would sidestep to achieve a distance that is somewhere about 75 centimeters. And then this effect asymptotically vanishes because if initially you are very far away, there would be no interaction between the two. And so the point again here was to find the expression of the interaction forces that would recover this behavior. And the beauty is that also in this case with simple forces, and again for the details I will just refer you to the paper. With simple forces, one can capture a lot of the statistical behavior of the system, like how much people would slow down as they approach each other in the avoidance process, but even the statistical rare events that here would be body-to-body collisions. So there are about 40 cases in our data of people that would get to a distance that is comparable to the body diameter, let's say 35-40 centimeters, and as we consider a mutual distance that grows, of course we have more and more cases, but the point is reproducing the cumulative distribution of this process, and again, a simple model is capable of doing so. So this made us very happy and encouraged to to build up further and further complexities. And so, if you would be interested, you will see that we have also paper in which we consider the one-to-n forces, let's say, the one-to-n avoidance process. Now, I mean, I want to get to the end of this talk, and so I want to discuss with you something very recent, that is, what if we want to attack even more complex scenario quantitatively, meaning what if we want to predict how a crowd in which we have say end-to-end interaction at play, how does such a crowd evolve? And well, we studied this problem in the context where this end-to-end interaction becomes relevant, that is in the routing problem. So imagine that you have a crowd that moves in a certain domain in which there can be obstacles and such, and then let's say the routing that the individual person would take is clearly dependent on the traffic. Let's say the undisturbed pedestrian might choose a given trajectory, but then as soon as there is the crowd around, then the preferred trajectory of the individual person would depend also on the traffic. So you want to get apart from the traffic, because if you manage to stay out of the traffic, your time to destination will be smaller. But actually everybody thinks the same, and so the system as a whole balances in such a way that the traversal time for all the particles is more or less the same. And what we did here is studying this routing problem in the presence of traffic, considering possibly the simplest scenario in which we have non-trivial routing, that is when we have a crowd that faces an obstacle and then needs to go past the obstacle. So in this case would be this pillar here. And there are two choices. One is to pass the obstacle from a main road, let's say path A here. And the second option would be to take a detour. Now, the point is that when you take a detour, you accept a penalty due to the fact that you are taking a longer route, but it can be convenient for you should the main way be too busy. And so the question becomes, when do people take a detour versus when do people take the main way? And which factors are at play? And to do this, we studied the problem in a variational sense. That is, we consider a sort of functional defined on the system, and then the observed configuration of the system would be the minimizers of the function. Okay, again, here we have our tracking sensors at play. So we would track all the people passing by this scenario, and imagine that in this case this experiment was run during a city festival. So a festival that was about 1 week long, and so all in all about 100,000 people passed by this experiment. And during this festival we would have people walking in the city, and well, it's a festival about illumination and design, so there would be exhibits about fancy and artistic illumination with new technology and so on. And so this is a yearly festival in Eindhoven, and generally every year we take the occasion of having big crowd to run our own experiment, and this is something that we did in 2019. Okay, so how does the system in this case look like? Imagine that we have snapshot of this type in which we have n people in the frame, and then a fraction of these n people would take the main way, and another fraction would take the secondary way. So we call people taking the main way, well, they are in the number NA, whereas these people are in the number NB. And so what I plot here is the total number of people on the x-axis, and then on average, I have in red the number of people that would take the main path, and then in blue the number of people that would take the secondary path. And so we see that when the density is low, all the people would take the main path, and then we have a smooth transition into using both the available ways. But again, this is the average routing distribution. So as I said, around well, 11 people in the image would have a smooth transition into using both. However, actually the system is much more interesting. As I said at the beginning, the system is rather stochastic. So not always when we reach 11 people or 10 people, we have a transition into using both channels. So what I report here in my plot is as a background shade is the probability distribution of people using the secondary channel conditioned to the people to the overall amount of people. And so what we can say here is that the usage of the secondary channel is highly fluctuating, but besides, it happens still rather frequently that people would jointly choose not to use the secondary channel and therefore to do a quite suboptimal decision transport-wise. So what you see here are instances of the case in which people jointly decide not to pick the secondary road and therefore to clog inside the primary road with deterioration of the overall performance. So we call this an herding effect. So you would, let's say, blindly follow who is in front instead of doing smart routing decisions. And then we ask, okay, imagine that we want to model these dynamics. Which are the crucial variational features that we need to introduce in the system in order to quantitatively reproduce the statistics of this routing behavior? Well, first of all, as I mentioned, we need a functional that couples the entire system. And so in our case, a functional that worked very well, we tried a number, was simply to consider the overall travel time by all the pedestrians in the system. So imagine the system would realize in a configuration for which the overall travel time as a sum of the travel time of all the people would be minimal. Second, we need to define what is the travel time of the people involved. And well, the travel time here is, of course, the distance that they have to walk divided by their velocity. And clearly, this walking velocity has scaling with the traffic. So the more people would be in one channel, the lower the velocity. This is called in the literature a fundamental diagram. So what you have here is the number of people in a channel, and on the y-axis is the velocity. The more the channel gets clogged, the lower the velocity, and therefore the higher the travel time. So now we have a stochastic functional that that couples all the pedestrians together, and the stochasticity here is given by the fluctuations in velocity. So as you can see here, the relation between density and velocity is non-deterministic, and this is due to the fact that there are variations in the system. This is what gives this. This is what gives the fluctuations here and my epsilon term here. Okay, we need a third form of stochasticity, that is also the way in which people could measure the length of the path is non-deterministic, in the sense that, well, in our modeling perspective, we have that whenever people would jointly choose not to use the secondary channel, and therefore everybody would use the primary channel, this would be the outcome of the fact that the secondary channel was perceived as extremely long, much longer than it actually is, and this turned it very unfavorable. And therefore, in order to minimize this cost functional, all the people would need to walk around the primary channel. Well, again, I think I stole a lot of your time, but let me say that such a simple functional enables quite accurate quantitative prediction of the smooth transition into using the second channel. But even the probability distribution function of the people in the primary or secondary channel condition to the overall traffic. And this is, again, in the direction of building models that reproduce the statistical portrait of the system. So having said this, I would like to conclude my talk and just go through the crucial point. So the perspective here is to establish an understanding paradigm for crowds, understanding in physical sense, and our interpretation of this is to try to identify and model features that are reproducible for the system, and therefore unavoidably for a system that is as random as a crowd, this feature need to be the characteristic probability distribution function of the system. And of course, to be able to understand and model the system in this perspective, we need to start from data, high quality, massive data as the only way to extract statistic features. Well, I also mentioned to you the fact that the free particle motion, so the very diluted dynamics, the simplest thing that you can do can be modeled with a bistable Langevin system, to which forces can be introduced to start modeling avoidance behavior and so on. And then, let's say, variational approach can be used to target more complicated traffic conditions. Actually, we worked on many more things, especially nudging and control problems, but if you guys are interested in this, please reach out our website, crowdflow.phys.ue.com, and you will see that there are pictures on our experiments there. And of course, you're very welcome in case of additional question. So having said that, I would like to thank you all for your attention, and I'm here for questions.
Thank you very much, Alessandro, for this very nice, very clear and interesting talk. Thank you very much. Are there questions, comments from the audience? François, you have a question?
Yes, thank you very much for a wonderful talk. Loved it. Absolutely. I just have one question. You view pedestrians in a sense as an atomic fluid. Would there be cases in which, considering the presence of pairwise correlations, so like a husband and wife, might be relevant? So rather molecules. I'm thinking, for example, for the herding process, if the 13 people who are in it have 5 couples, maybe that's the reason.
Yes. Okay, thanks for this question. Very, very nice question. Okay, so this, let me say 2 things. That both in the force perspective, this has been investigated. So, well, there are papers not by me, but by, for instance, a group in Japan that is dealing with the same topic, the same problem, with a guy named Francesco Zanlungo. They would study the potential for groups. Now you mentioned, the biatomic molecules, and you can have, let's say, triatomic molecules, and it's possible, having enough data, of course, to study which kind of potential this pair of atoms or triplet of atoms would have in order to stay cohesive. And I fully agree with you that the flow is in principle not a single atom flow, but it's it's a distribution of groups of different sizes, which would give different friction problems inside the flow. I must also say that investigating groups is at least for me an open problem. It's like one of my next open problems. So understanding which kind of distribution of group size you have and how this influences the overall flow is something that I'm very interested into looking into, but that we have not looked into yet. Also because there is a technical difficulty in extracting groups automatically from this sort of data. Yeah, so having ground truth of what in our flow was a group and what was not a group. Yeah.
Yes, of course. It's all much more difficult when you look at groups. But I was wondering if you had seen these effects in your data. So it's not obvious in any case.
Okay, I must say that in our data, what we looked at was the effect of non-groups. Generally, as I told you, the free particle, the interaction, and then when we moved to the variational problem, we averaged out the effect of groups. So there is not a fine perspective on groups.
Thank you very much. Yes.
Yeah.
Okay, I think there's a question from Bernardo.
Yes. Sorry, well, I enjoyed very much the talk.
Yeah.
But your first slide showed huge crowds, probably some border between two countries, one of them at war, whatever. So your treatment really has to do rather with crowds at airports when things are normal.
Yeah.
But I would think that the main utility of these research would be to understand how to control crowds, sometimes in unruly conditions or overcapacity of installations. So what are the limits in terms of what kind of environments you want to understand and to improve, perhaps?
Okay. Thanks for the question. So let's say what we are really doing now is to study control problems for crowds in, let's say, everyday density level. Okay, which means 1 person per square meter, 1.5 people per square meter or so. And the idea is that although these conditions are in many cases not dangerous, at least in Europe, there is a strong need to be able to steer crowd flows at this density. So to have the flow going in specific direction or to distribute in specific way, again, for this problem of having limited space. So imagine you have a train station and you would like your people to be equally or uniformly distributed on the platform and not to clog in any specific location. And this is because you want your people to be able to walk throughout the platform, not to clog, and let's say, and you want to use all your available space. Yeah, so the question becomes, how do I use my environment to nudge people to acquire this density distribution? And this is the type of research that is going on right now. So, for instance, how do we use illumination? How do we use sound? How do we use stimuli in order to achieve given flow conditions or given stationary conditions? And we do this generally at density levels that are, the everyday life density levels. So then, still non-risk density levels. And this with the purpose of try to avoid risky situations. So to nudge the crowd in safe condition in order to keep it in safe conditions and not to have the need of calling stewards and police people to help.
So you would not consider, say, Heathrow Airport?
Well, why not?
Well, because it's a horrible mess over there.
Yeah, but I agree.
Well,
I mean, let's say our train stations are also pretty busy. But okay, we're still talking about densities that are 1.5 people per square meter. I mean, even at Heathrow, when it's very busy, I mean, you generally don't have densities that are above this 1.5 people per square meter. I mean, so this is the normal the normal level of crowds. Actually, it's even hard to have densities that are above 0.5 people per square meter. I mean, they're already in exceptional conditions, at least in Europe. Now, I don't know about the typical crowd in Mexico, I must be honest. So you might have much higher density every day. I don't know. But yeah, for us, a busy train station is 1.5 people per square meter. And then people would start feeling the presence of a dense crowd.
Okay. Are there further questions, comments from the audience? If not, I have two questions. The first one, rather technical. The trajectories of these persons, which you measure with this Xbox Microsoft cameras, how long have they been? They have been about 5 meters, 10 meters?
Well, depends on the setup. Again, the picture that I showed you there was for trajectories that were about 4 meters long, and this was done in 2014. Now we have setups that spans 300-400 square meters. So imagine huge grids of these sensors in which we would track continuously people for like 20 meters or 30 meters.
Because my question goes in this direction that I had the impression that you, on the videos which you showed, that the trajectories have been rather short. So my question is, these avoided collisions of the people, when I, how to say, when I look much meters in front of me, sometimes I can avoid a collision just many meters ahead. I can see that there are some people coming and I can avoid them very slightly, my trajectory. But when I'm looking on my smartphone and I'm walking in the train station looking on my smartphone, then I think these things happen that suddenly there's someone coming in front of me and I have to avoid him or her abruptly. So my question is, can you distinguish these effects, or do you just focus on the latter one by considering shorter trajectories?
Wait a minute. Okay, so well, once more, what we studied was sort of transverse function. So how does the distance between two people, how does the initial distance between two people as they enter in our observation windows change as they basically are closest in space, and then also when they exit? So of course our let's say our perspective on the problem is limited by this window. So all our forces are sized given the fact that there have been possibly prior effects, and then we studied the dynamics as they enter in our observation window. So in principle, yes, the forces could span
I see.
longer distances, and then our modeling is limited to our. Also, imagine that now we have much larger setup, and so we are actually running similar analysis onto even larger scales. Now, about the mobile phone case. You might say that there is you might know that there is a dedicated study on this, on how people get distracted when they have a mobile phone. So and this is actually the work that won the other Ig Nobel last year. So that was about the statistics of collisions when people are distracted by using a mobile phone. So when they are incapable of doing long distance decisions.
I see. My second question is, did you continue with these measurements during the COVID pandemic? And did you observe any changes regarding the avoided crossings in the pandemic? If the people are avoiding each other more?
Well, yeah, I mean, unavoidably. We have a paper that is about distancing statistics, pre-COVID and during COVID, and how the distancing statistics changed over COVID. And in this case, the data were based on sensor tracking throughout entire platforms. So we're talking about platforms of 200-300 meters at times. Well, I mean, of course, well, we could observe time trends, like the fact that the first 2 weeks after the pandemics, then people would keep very, very large distances. But you know, actually, after already a couple of months, at least here, the degree to which the measures, the social distance measures were observed was already significantly lower. And also, you know, you would observe that in the crowd there are, you know, random events. I mean, random presence of people that would systematically infringe distance with many other people, like I mean, that would systematically ignore the fact that they need to follow the social distance, getting close to huge number of other people. So, I mean, you can study all sorts of these statistics, but of course, I mean, yeah, you can definitely, but I assume you can expect this, you can definitely see a strong variation in all this distancing pattern because of COVID. Yeah.
I see. I see. Okay, thank you very much. Are there further comments, questions from the audience? Yeah, then Alessandro, thank you very much again. Thank you very much for joining us today, at least virtually. It would have a pleasure for us to have you here in person. And yes, in my impression, the things are getting much more crowded here in Mexico, in particular in Mexico City, comparing to the Netherlands or to Germany. This is
I can expect. All right. Thanks. Thanks again for the invitation.
Okay. And thank you very much, and see you next week. Bye bye.